Hey everyone, this is Matt with Learn Everything About Design, and in today's video, we're going to be walking through this example of designing a fairly simple PCB inside of Fusion. Now, this isn't the first PCB that we've done. We've done a couple of little examples on this channel over the past couple of years. Recently, there was a bonus video from our course on learneverythingaboutdesign.com where that bonus video talked about making your own components in the library and basically putting 3D models to them. We also did a video that was, God, what did I call it? 5 P's of product design. And it was basically, I don't know if you can even see this. God, everything's tangled over here. It was basically this LED coaster. And so there's an FSR or force sensitive resistor. And basically this is something I built so that at night I've got a night light, and when I when I set a glass down on it, it gets dim, and we got the ability to turn the LEDs off and change the colors and all that sort of stuff. Now it has basically an Adafruit Cutie Pie on it. I use this form factor of boards for all of my projects, almost all my projects. FSR, and then it's just got a couple of push buttons to change the color or to turn it off. And so this is a pretty nice project. This was something that I built, again, just kind of for myself. And I do use it. I don't use it as much as I used to. Sorry, I got to reset these cables. But it was a project that we did with PCB I. And so I think that I get questions from time to time about printed circuit board stuff. And so every time I've done several boards just for myself. I thought this was a good one where we could work through an example, talk about some basics and so on. What we're not going to be doing in this video is we're not going to be going through setting up our own components. There's going to be a share link for the library, which will have everything in it that you'll need, everything including things like the voltage and ground symbols, the custom ones that I have. So for example, this is an 8-position connector that I got for a headlight dimmer project I was working on, and you can push wires into it, and then the Cutie Pie symbol and so on. So again, we're not going to be doing that in this video because I'll put a link to the reference video that kind of goes through that. But we will be walking through setting up the schematic and the layout, the board design, having the 3D model. I even designed a little housing and 3D printed it for my display in the garage, or the control box in the garage. But so we'll be going through those basics. A couple of things that we need to talk about. And so if you want to follow along and you want to skip this initial sort of discussion rant portion, then check the chapters and you can jump ahead to when we get started. But there are several things that we need to talk about. One is the fact that this is a personal project, which I just made for myself. And with that, I purchased the boards myself. This is not a sponsored video, but I did use PCB I. And the reason I say that is because a lot of times when we do affiliate videos, there's always a sort of question, and I get it, whenever I'm watching a YouTube channel and somebody's sponsoring something, I think to myself, like, oh, you don't actually use that. So anything that you see on the channel is something that I do actually use. And so I think that's always important, but it can get lost, especially if you only ever see it in an affiliate video. So I've used PCB I for a few things now. This board was one of them. I designed it, I purchased it. I didn't even tell my contacts at PCB I that I was doing it until after I had the boards. And so I decided to spend my own money on these boards with PCB I. And the reason I'm kind of saying this is because I do need to talk about the current state of how much things cost to get produced and how much they cost to get shipped and taxes and so on. Now on this channel, I try really hard to not just make it a money-making thing. So for example, in the YouTube settings, I turn off political ads as well as gambling ads and some other things. And those are definitely hurting the videos getting out and getting advertisers to pay in front of the videos. But I am just sick of watching political ads and gambling ads and all these other types of things. And so I make a conscious effort to toggle these things off, even though I know that financially, advertisers would pay more to put them in front of the videos. And so, I don't want to talk about anything political on the channel, but I will say that with the current state of things, because these PCBs are coming from China, there is additional fees that you will have to pay if you order, whether it's a CNC machined part or PCBs or injection molds or whatever the case is. And so I want to talk about those prices in this video as well. So these boards, I ordered 5 of them. I almost always order at least 5 or 10 boards whenever I'm making anything. It doesn't hurt to have extras laying around. And every time I build a board, I always try to add extra functionality. So like this proto area, for example, any available output that was not being used for this board design has been ported over to this little proto area. Even 5 volts, which comes in from the voltage regulator, it goes to the logic level shifter, but I also sent it to this via. And the reason for that is because if I want to power the board with the 5-volt regulator, I have to use a diode and sort of filter the power. But I have the ability to do that, so where I don't need to use the USB-C to power the board. And so anytime I'm making a board, there's real estate on these boards. This one could be a lot smaller, but there's real estate on the boards, and there's no reason not to give it more functionality when it's just a personal project. And so I try to do that anytime I'm designing a board. But the point of this is that I ordered 5 of them. It was $5 for the boards, so $1 a piece. $25 to ship with DHL, and another $21 in import tariff tax and processing, essentially. So my guess is that it was about $1 in actual additional tax on top of the $5 of boards, and then a $20 processing fee. And so while in the end, $50 for 5 custom boards isn't that bad, if I had ordered 1 board, I would likely be paying exactly the same thing. So I'd be paying $50 for 1 board. Or if I ordered 10 boards, it would likely be pretty close to the same thing. And I think that's important because if you're ordering, you don't actually know these extra fees until they hit US soil. And then the shipper or importer, in this case DHL, will reach out and say, hey, if you actually want your thing delivered, you owe us more money. And so that kind of sucks. But it's something that we need to be kind of aware of if you're going to be ordering these, especially if you're building your own projects. The other thing to keep in mind is I know a lot of people are now getting access to desktop CNCs like Carvera. And Carvera actually reached out and wanted to send me one, and I denied it or turned it down because I didn't think it would fit with the types of parts I need to machine. And so again, it comes back to the sponsored videos and things like that. But you can custom make your own PCBs with machines like that at home. And there is a cost associated with the machine and the time involved to do that. And I would say that the results are not as good as professional built PCB, but it is possible. Now, other companies that I have used in the past, like DK Red, which is DigiKey's rapid sort of PCB service, they are more restrictive in the size of boards as well as the setting, not the settings, but the specifics of it, like the copper and the thicknesses and the color of the boards have to be red and things like that. So when I did quote through DK Red, I believe it was about $90 for 5 boards shipped. Now, of course, we get around the import tax, but it was also a slower turnaround time. And so almost double the price, and the lead time was, I think, 2 weeks, whereas with PCB Way, it was a week. And so it's always something that we have to consider. Now, if you have a bigger project and the parts cost more than $5 for PCBs, then you're going to get hit with a higher a tax depending on what it is. Then you have to kind of weigh those options. But for this project, again, it was just a personal project. I thought it was important to kind of share those numbers. Now, I don't have any association with DigiKey or DK Red. I have produced a few boards with them, again, for personal use. I was working on a headlight dimmer project for my KTM. I have a 450 SXF that I street titled, and I was trying to make my own sort of headlight dimmer, and I included GPS and an SD card slot and all this other stuff. Didn't end up working out. I had some issues I couldn't quite sort out, and I just bought an off-the-shelf option. But I did go through DK Red for that, and I was very happy with the service. But it's just something to keep in mind, again, turnaround time, costs, duties, and taxes, and things like that you have to keep in mind. Okay, so now that's kind of all the ranting that I wanted to get out of the way 10 minutes later. So just to kind of wrap that up, be aware that when you order something from not just China, but pretty much anywhere, right now there is additional fees that you will have to pay. And a lot of times it is likely going to be a surprise to you because the exporter, in this case PCB, doesn't actually know what that is until it hits the DHL facility in the US, and then they assess and say, hey, this is what you owe extra. All right, if you have any questions on that, feel free to leave them in the comments. As I said, I don't ever really want to talk about anything political on this channel. I turn the political ads off, but it's just something that we need to keep in mind, especially when ordering these types of parts. All right, but again, any comments or questions on that, feel free to leave them in the video, or feel free to email me as well, support@caducator.com. All right, so with all that out of the way, what are we building and why are we building it? Well, this is a logic level shifter. And so to give you a little bit of background, when I originally built this project for my house, I ordered 1,500 RGB LEDs in 50 LED strips. And so these were outdoor rated. They were supposed to be for, displays and things like that. Now, though it had, the cables had power, ground, and signal on them. And after doing a bunch of reading and testing, it was clear that I couldn't just run the 12 volts through all of them for the lengths that I wanted. They actually wanted me to run secondary power and inject it into each connector. This was from the manufacturer. And so ended up having to do basically a extension cord that paralleled the entire thing and injected 12 volts in at every 50 LEDs. And so this was a massive pain. And the second thing that ended up happening is that the signal coming out of most microcontrollers is at 3.3 volts. So when we're trying to do like a PWM for an RGB LED, so we can program what color it's going to be or what's happening, that signal at 3.3 volts works okay for a certain amount, a certain distance it has to travel. But once we get past like the first 50 LEDs and we start to have like 300 or 400 LEDs, what ends up happening is, as it's like a bad game of telephone. As that signal gets down the line, it gets distorted, and then you get LEDs that are just turning on random colors, or they're stuck and they're flickering, or just weird things start to happen. And so the way to get around that is either to use a controller that sends a higher voltage signal. So I had pretty good luck with something like an Arduino Uno. But with these smaller microcontrollers, basically the solution is to use a logic level converter. And so what happens here is we run 12 volts in. I've already got 12 volt power supplies. Run it through a voltage regulator, which takes it down to 5 volts. And so then we feed 5 volts into this logic level converter. And what happens is each of the 4 available pins that we have is grounded, so they all share a common ground. This is another big thing that has to happen with the signal. And then we feed in the 3.3 volt signal from the microcontroller, and then it sends that signal out at 5 volts. And so that is the way that we can get a clean signal out across hundreds of LEDs. There may be a different way to do it, but when I first set this project up, it was kind of like November, and I was like, yeah, sure, I can definitely do this. And then obviously we're getting close, November, December's rolling around, and I don't have lights working yet, right? So kind of had to rush this. This is, 4 years ago at this point. So fast forward to this board. Why am I making this now 4 years later? Well, when I first built this, it was hacked together. And so I had just some proto board laying around, and I wired it up, just a mess, bird's nest of wires. And it worked okay for that year, and then it started to fritz out. So maybe last year, I think I did a better version of that. But the problem is we've got a lot of things like common grounds that have to happen from this chip. And so it ends up with like long sections of a bunch of wires soldered together. Whereas on a PCB like this, all the blue area is a ground plane. And so it's just much cleaner and better and more consistent to have a dedicated circuit board. And it let me do a couple of other things as well. And so on the 3D version of this, we've got these connectors, which I originally had laying around from my headlight dimmer project. And these allow me to just basically strip the end of a wire and push it in. And it's like a push lock. And so to remove it, there's a little tab here that you can stick a small screwdriver or something in and release it. But it's got a really good solid contact. And then you can get basically a good connection between those pins and the rest of the traces that have to happen. So this allows me to do all of the signals, basically the signal and ground wires that have to go out to each of the 3 individual strands that I'm controlling. And it lets me go to the voltage regulator, which goes into the logic level converter, and all the signals can come in from available ports on. In this case, I'm using an ESP32S2 version of the QT Py. Now, part of the reason for that is it has Wi-Fi on it, and it's really good for IoT. And so I've got it set up on the Adafruit I/O, so I can connect to the board and do different kinds of things. I'm still working on some functionality there, but that's one of the reasons why I'm using that version. But the QT Py format, you can get SAMD21 boards or a bunch of different versions of ESP32 boards. So it's a pretty nice package. And the other thing that this board, the PCB let me do is toss on a proto area. So any of the other pins that weren't being used in going to this. So essentially I've got 3 signals that I need to go from the microcontroller out. The 4th available option, because there were 4 available on this logic level shifter, essentially what I did was I still used it and I sent it to this extra pin up here. So if for some reason I need to program a 4th strand, I can put a signal here and the common ground here, and I can run a 4th strand if I have to. And so it gives me a little bit of flexibility. Or if something comes up and I need to also control other things, like maybe I want to incorporate a push button, or I want to incorporate something else into the display. Every other available pin that I have here, so basically A0 through A3, and then over here we've got the transmit and the serial clock and serial data lines. Those come directly to these pins as well. And then I also took the pins for 3.3 volt directly from here, and then 5 volt. What I actually ended up doing is I put a via in here. And this, we may or may not do this, but essentially what we have here is we've got the 12 volt, which is coming from the voltage regulator, goes to that pin. 5 volt from the voltage regulator goes to that pin. And then I took an extra line out from that pin to this via. And so what this lets me do is it lets me put like a Schlotsky diode or something between that via and the 5 volt pin, which is tied to the microcontroller. And the reason for that is because maybe I want to power the entire thing off of the 12 volts from the power supply and not use the USB-C for that. And so again, anytime I'm designing these kinds of things, I'm not an electrical engineer. I learn kind of just by doing and playing around. I try to make them as flexible and robust as possible and try to think of any potential scenario that I might need to be able to use this in. The other thing that I did when we did like the coaster that has the LEDs on it, I soldered the boards directly, or I soldered the microcontrollers directly to the boards. When I did the game controller, I did the same thing, and in trying to keep everything as narrow, as thin as possible. I don't have the electrical engineering knowledge to be able to design a board with my own microcontroller and all the extra little pieces that need to go into it. I could probably figure it out with enough time, but it's just so much easier for me to use off-the-shelf components like this and then connect it to the rest of the stuff that I need to do. With something like this, what I ended up doing was just putting in essentially jumpers or connectors and then soldering the pins to the board, and then I can plug it in and I can swap out different variations. And so I've got two of these where one I'm playing around with Adafruit IO and testing out different things I can do, while the other one is actually controlling the lights on the house. So all of that's out of the way. That's quite a lot, but now you can hopefully understand what we're doing and why. The way that we get started, the first thing that you want to do is go to the link in the description of the video and upload the library. Now, I have the library here because I built it in the data panel and saved it there, but I'm going to go through the same exact process. And so what we're going to do is we're going to upload, and I'm going to select, this is actually a mountain bike fender that is also a project that you may have already seen. I don't know when these videos are going to hit. So basically find the Fusion library. It's a download link. We're going to upload it into a folder in a project. With the libraries in the electronics workspace, they are generally, there are a couple ways that we can do this, but generally what you have is you'll either have a shared library, or you'll have like a managed library, one that's managed by Autodesk. Potentially there are some other vendors that manage their own libraries, but usually it'll be either Autodesk or Eagle PCB. Eagle is the PCB stuff that's actually been incorporated into Fusion, or ones that you build yourself. And so in this case, we're going to use one that I built that has everything we need in it. Once we have that, we're going to start a new electronics design. Currently, I have intent-driven design turned on, and so when I go to select new, I will pick electronics design from here. If you do not have intent-driven design turned on in your preferences, you can go to the File, New, and go to New Electronics Design. They've also added it to the workspace picker. In some cases, if you don't have, I'll just go to a new design. So if you are just in a normal design in Fusion, you also have the electronics option from the workspace picker. And so all three of them are going to go to the same place. It doesn't really matter, but we're just going to do a new electronics design. When we do this, there are basically three things that we should be concerned with. We've got a schematic, we've got a PCB, and then there is going to be a 3D model that's associated with it. But then there's sort of this like third file type that's going to connect all of them together. And so if we look at the example here of the Christmas light, the one I was showing you here, we've got essentially the schematic, which is like the blueprint of how everything gets connected. We've got the layout of that, which is basically putting everything onto a circuit board. And then there's a 3D version of that. This is the top and the bottom of it. And so all three of these different pieces are within this project. And the project is like a connector, like for an assembly, it's just putting all the pieces together. So if you go into your data panel, you're actually going to see all three of these, as well as that fourth file type. I'm going to close the untitled solid document. I'm going to go back to here. And so when you start a new electronics design, you have the ability to reference a current schematic. And so if you're trying to link multiples together or repurpose a schematic and maybe make a different board design or something like that, you have the ability to do that and link them together. For us, we're going to be starting from scratch, starting with a brand new schematic. So just select new schematic. From here now, we need to incorporate or add our library. And so on the right-hand side, we've got basically this tab interface here. We've got place components, and this is going to be a list of components that are available in any library that you have deemed active for your design. And so what we want to do is we want to go to the manager, which you can get to from here. You can also go to the library tools and go to up here. It's going to take you to the same exact place. These little blue active check marks or things over here, these are libraries that are going to be active. And this isn't all of them. These are just ones that either I own. So for example, these lead PCB logic level things and lead library controller and so on. When you see the little icon of the three people, these are ones that are stored in this design, essentially. Now, at the top, you've got public libraries and you've got private libraries. I have access to any private ones here, but there are public libraries that are either managed by Fusion or managed by third-party resources. Some of the third-party resources are going to be better than others. For example, a lot of times when you go into some of these third-party resources, they may not have a solid model associated with the components, which means if you really need to have a solid model and have everything in a 3D model version of it, then you're going to have to do a little bit extra work. You're going to have to copy those library components to your own library so that you can connect the dots. But you will notice that there are some here like BeagleBones. Now, if you're using BeagleBone or Arduino's boards, which now they've been bought by Qualcomm or something, or Adafruit or SparkFun, you will actually find quite a lot of resources. So for example, I'll just download this. In many cases with like SparkFun and Adafruit, you will have a lot of great resources for boards that they have designed or components that they've designed specifically. Adafruit is a great example. And so the 3D model of the Cutie Pie, for example, came directly from a PCB file that Adafruit made publicly available. So you can actually go in and take a look at their PCB and so on. They're not connected generally, so the 3D model that you can download won't be connected to a schematic that you can necessarily use in your designs like I have set up, but you do have access to those things. What we're going to be focused on is incorporating a specific library. And so this one right here, lead PCB logic level library, this is the one that I just uploaded. It's 8 o'clock now, so that's the one I just uploaded. This is when I created it earlier today. Originally I had intended to start recording earlier, didn't quite work out. But you can see the packages that are in here. And so there's the 8-pin connector that we're going to use. There's two versions of it. I'll talk a little bit about the differences there. There is the Cutie Pie footprint. You can see the 3D model associated with it. There is a couple of different components here. So these are the voltage regulators, and there are different footprints for those. And so this is the one that we're going to be using, the TO220. And there is also this one here, this DIL14. This is the logic level shifter. And so once again, these are the packages. If we go into components, you can also see that we've got the ground symbol and the power symbol. Those don't actually end up having a component portion of it that will be visible on, let's say, a 3D model, because what we end up doing is we create a ground plane and we name it GND for ground, and then the entire ground plane will be associated with that symbol in our schematic. And so the big thing here is make sure that you upload that to your data panel and then you activate it so that we can use it in the design. Once we only have a single library active and we close this out, we should only see, or we can filter by only that specific library that we want to use. And so now we've only got the components that we need for our specific design. And so now we can get started placing and building out essentially what the circuit should do. So the first thing that I generally will do with these is I will place the big components and then I will go through and figure out all the extra little stuff. And so, for example, the cutie pie. Now there's a drop down here. There are two different versions. I'm gonna take the second one and drag it over. The reason I'm taking the second one is even though the cutie pie, so I'm just gonna left click to place it and then select done. So even though the cutie pie is a standard footprint across a lot of different boards that Adafruit has made, you will find if you go to, or you should at least double check, that the SAMD version or ESP versions, a lot of times you'll find that the pinouts may be different. And so you should always double check. I suggest making your own components and not just using mine, but you should always double check that. And so with the version that I made on the, once we get to the PCB layout, I just have a basic block where the USB and the cutie pie or the JST connector is. And then the 3D model has the graphics and stuff applied to it, which is again directly downloaded from Adafruit. All right, so we've got our microcontroller, which we're going to have all of, with the microcontroller, we're going to have all the different inputs that we need. The other thing that we need is we need to have our, basically our voltage regulator. Anytime you see a drop down here, there are going to be multiple options. So the one that we want to pick is going to have a 3D model with it. It's going to be the basically the TO220, which dictates the package, and that's going to be the basically this large regulator with the 3 pins on the bottom. Anytime I'm making something that I have to solder myself, I try to pay very close attention to these. You can do surface mount soldering at home if you're not very comfortable with it, or if you don't have a really good soldering iron with some very, some very good tips on them. Then you should just stick to the through hole stuff, honestly. The soldering iron I have isn't great, and it doesn't, the heat, it doesn't actually go all the way to the tip, so I end up having to use the side of it. Anyways, so then we're going to take that, we're going to drag it in. When you're placing these, you can use the right mouse button to rotate it around, and you'll notice that it kind of goes through this. There's also this mirror option. Really, at this stage, what we want to focus on is getting things in a place where the orientation and rotation makes sense for all of the traces or the nets that we need to connect. And so I'm just going to place that up in the upper right hand corner. Pin 1 is kind of going to the left. VI is voltage in. VO, pin 3 is voltage out. That's going to be our 5 volt out. So it's 12 volt in, 5 volt out, and ground. The other things that we need are going to be our wire to board. So I'm going to drag this, hold down the left mouse button, drag it down. I'm going to hit the right mouse button to rotate this a couple times. I want 1 at the top, so basically pin 1 at the top. I'm going to say done. We also have this 7407 quad. I tried to bring in just the components that we need without a lot of variance, but the voltage regulator, the cutie pie has 2 variants, again, because of the nuance in the pinouts. If you're not going to make this board, you don't have to stress too much about it, but we're going to go ahead and drag this in. I'm going to place this under the cutie pie and select done. And now that's essentially all the components. We need a bunch of powers and grounds, and then we need to start connecting things together. And so, oh, there is one more thing. Sorry, the proto area. And so the proto area, I'm going to go ahead and drag this over. Let's place it over here on the left-hand side, maybe like that. And so let's go ahead and pull this over. The proto area, again, when we get into 3D, and actually let's go ahead and switch to the 2D PCB. The proto area is going to be essentially just a section where I've created a bunch of vias that we can put components in. So they should have the same hole size as most through-hole components. And so you can see here that I've made some labels for things like A0, A1, A2. And if you notice, if we zoom in, you'll notice that A0, A1, A2 are the names of those pins. Anything that has basically the automatic generated name $$64, these are not going to automatically connect to anywhere. anything that has a pin name, and so for example, A0, and if we go to the cutie pie symbol A0, you'll notice the pin is named the same. Anything that has that same name by default is going to try to connect together. And so once we start to, well, I shouldn't say by default it'll connect together, but once we start to connect these things, so the A0 to this pin, what's going to end up happening is it's going to create an air wire that will determine or dictate how these things are going to get connected. Let's just do a simple example here. So this net means we're going to connect things together. So we're going to left click here, start to drag out to the left, and then I'm going to come up a little bit, left click, and then I'm going to snap it over to this one and say done. And then when I push this to the 2D PCB, what we should see now is we've got what is considered an air wire. And the air wire just is basically a visual representation saying this one here is going to connect to this one here. And now you'll see that it says A0 and $1, and this one says A0 and $1. And so essentially, the name of that trace, or that net, I should say, if we go back, if we click on this, and we go to the inspector, the name of this is N$1, this reference designation. And so now it's saying that these things are connected. And this is one way that we can ensure that, for example, on our proto area, we can make sure that this A0 is connected to that one because we have them named here in these symbols. Another way that this happens is like with the ground pins. Once we start to place ground pins and we create basically a layer of the board that's named ground, GND, it will automatically connect all those things together. So we won't have to run traces all over the place. It will know that it can just basically connect those pins directly to ground. So this is the process that we're going to go through. The pins that we're going to use for the actual design, again, if you're not going to make this, it doesn't matter, but we're going to use MO, MI, SCK, the serial clock, and RX. And so these can be used for other sorts of things if you know about I2C communication, or if you want to use any of these pins for something else, then you certainly can. But that's what we're going to do. So we're going to be taking those down here. So to just kind of get comfortable with this, let's go ahead and start to connect some more of these. And what's kind of important here is keeping things as clean as possible. And when I say as clean as possible, it's because we don't want it to get to the point where it's hard to read. What we should be able to look at this, and we should be able to follow it and understand where things are going. And so spend a little bit of time trying to make sure things that are like a consistent distance away. And then as we come over here and start connecting, we've got the serial clock. We'll come up here, and then TX, and then ground, 5 volts, 3 volts. We're going to have to kind of wrap around to get 5 volts and 3 volts. Ground is going to be common across because we're going to put some ground symbols here. We'll deal with that in a second. And extra is going to end up coming over to the 4th port in our thing over here. So we're not going to worry about extra just yet. We'll come back to that. Ground we'll come back to. But 5 volts and 3 volts, let's go ahead and wrap these around. And so what I'm going to do is I'm going to leave enough space because I need to put a ground symbol over here. So I'm going to come out and kind of come over. I'm going to come out a little ways over here and connect to that 5 volts. And I'm going to do the same thing for 3 volts. Again, trying to keep things consistent, and you just left click if you need to get it to change direction. We'll put it there. You can get traces to cross over. If you click on one while you're creating a new net, it will automatically try to connect things together. And so you do need to be careful there. All right, let's go back to our library, and let's continue by adding some ground symbols. And so what we want to do is we have GND. We're just going to drag this out, and we'll place it down here. The value is going to be GND. This is going to be important. So anytime we're using things like resistors, it's going to ask us for a value. With ground and with power, it will ask us for a value as well. And that value is important because that's what's going to sort of connect everything together. We're going to have another ground over here. And so I'm going to hit the right mouse button and flip it vertical. And so that way it just stays a little cleaner. And then I'm going to right click twice. I'm going to put this one down here. You can also, if you want to, like point it out to the left, it's like this, so we can just draw a net straight to it. Again, keeping it far away because some of these are going to have to turn around. Any of these that say OE on them, we're going to end up grounding them. And so I'm going to go ahead and put one there. Right click twice. I'm going to do the same thing for 4 OE and 3 OE. And so now we've got ground going out, 2 OE, 1 OE. Those are all going to be grounded. We've got 4 OE coming out and 3 OE. Those are going to be grounded. And then over here, let's right click. Basically, we're going to have several of these that are going to be grounded. And so pin 8 is going to be 12 volts in. Pin 7 is going to be grounded. And so I'm going to start maybe like right here. So pin 7 will be grounded. Then pin 6 will be grounded. Pin 4 will be grounded. And pin 2 will be grounded. And then I'm going to say done. That should be all of it. And then next, let's go ahead and take the voltage here. And so I'm going to drag this one over here. That one is going to be 12 volts. And if you want to change the value on this, if we click on this and go to the inspector, you'll notice the value here is 12. We can say 12V if we want, and that'll change that. So that's going to be important because we've got 12 volts coming in to the voltage regulator, and the 12 volts is actually coming into pin 8. And so what we could do is we could just simply run this VI over to pin 8, and that would work fine. But sometimes when you're making these layouts, you don't really want to be running all these traces all over the place. Now, it makes sense if we're connecting pin TX to something specific, but for power and ground, typically what we want to do is we want to keep those as short as possible. And so what I'm going to do is I'm going to bring another one. I'm going to right click over here and place it, and we can say 12V, which will make it the same. You see there's a little drop down. We can click on that. And because those values are the same, I used it from the drop down, it will automatically know those are the same. So as we bring 12 volts into here and we bring it into here, it will know to connect those when we move to the 2D PCB. And so now we can go to our nets and we can connect those together. I'm going to connect pin 8. I'm going to left click and then click there. And then again, we need to connect the ground. I think I got a sneeze coming on. Oh. Again, all the things that I don't have to worry about when I don't have the webcam on, because I can just pause and sneeze and just carry about my business. All right, so let's go ahead and do the nets. All right, so pin 1 is going to go to 1Y, which we're going to connect in a bit. Pin 1A will go to MO. And so basically what's happening is MO is going to come in, bring the signal in at 3.3 volts. It's going to go out at 5 volts, which will then come over to where we're connecting the actual signal to the lights. And so that's what's happening. And so you can just start connecting all these things together. So we've got this ground, this is grounded, that's grounded, that one's grounded, ground is grounded. This one here goes to ground. And then I think I said 7. That one's grounded. And so this is power and ground in, and then 6 is grounded. I gotta look at a reference sheet I got. And then 5 will be a signal, 4 is grounded, and then that should mean 2 is grounded as well. There are other options that we have for nets. So for example, if you, I makes the most amount of sense to just have it be right angles, but if you want it to do something different, you can. I do not suggest kind of doing freestyle signals like that. They typically will work better like this, but if you have a specific reason, you can change it in the net diagram. Oh, I forgot one. This one has to be grounded. All right. And so now we have got to connect a couple of other things together. All right. So we've got, let's go here. So 12 volts is coming in from the power supply, and ground is coming in from the power supply. So this is taking the ground from the power supply and making it common across the board, which means that we're grounding the microcontroller to it. We're grounding all of our outputs, which will be our signals going to the lights. And we're grounding the voltage regulator that's going from 12 down to 5. And we're grounding the, in this case, the logic level shifter. And so having that common ground plane across everything is what makes this much more consistent than me just hacking it together. And so now we can start to connect the power and the rest of the signals. And so it's going to start to overlap if I do this, and I don't really like the way that looks. So I'm going to come over, then down, and then back over. And then now we want to connect basically our signals. So we've got our microcontroller, and we've got basically, again, 1A is going to be the input to the logic level shifter, and 1Y is going to be out to this over here. And so we're going to start with MO. You have to think about how far these need to go out. You'll need to leave a bit of room. They will have to cross over depending on how you do it. And so if you ever have to go back and change it, that's fine. And then this one over here, it's going to get weird because of this. Here, let me do this. So I'm going to box select these two and just move them a little bit. And then I'm going to take this and I'm going to move it over here. Move that over there. Maybe that'll give me a little bit more room. All right, so we'll come over here. I'll come down over around the board, up, and connect to that. All right, and so then 2A, we're going to come from MI. And I'm going to cross over these grounds and go there. And then 2Y, I'll come out. Again, kind of keeping things close. I'm going to have to cross over at some point. As long as you don't click on that, it won't try to connect them together. If you do, if I click there, you'll notice it put a little dot. And essentially what it did was it is now combined those. So I'm going to do Control Z to undo that one. So you want to be careful and not connecting those. Let's go ahead and click there. We'll carry that one on. Cross over. Start to come up. And then go to 2. And then SCK is serial clock. That's going to go to 3Y. Now, they end up flipping a little bit. So if you have to cross over here, for example, and come down, so we want to go to 3A, and then 3Y is going to come out. I'm going to cross over here and go to that pin. The fourth one is the extra, so that's what this pin over here is. And, oh, I forgot a ground here. I need to ground that. So what we're going to do is we're going to take this RX, and that is going to be 4A, come in there. And then this 4Y is going to go over to this extra. And again, they can cross over. It just kind of depends on how you want to keep things clean. I think maybe right there. I think I'm going to hit escape. And then I'm going to move this ground to the left to free up a little bit of space. And then we'll carry on from there. And so that'll let me come down to there and over. All right. So with the ground over here, if we want to, we can select another one and just use Control C and Control V and just place it right there and connect that. We definitely need to have that board grounded. When we're dealing with signals like this, it is extremely important that we have that common ground. And so if you are doing something with just one LED or a couple of LEDs, it might not make a difference. But if you're trying to send a signal across hundreds or thousands of these RGB LEDs, the signal integrity is a super important thing. The timing of everything is important, and that has to do a bit with the code. But again, making sure it's a common ground is important. All right, so now everything looks like it's connected. So we've got 12 volts in ground coming into pin 7 and 8. And then each one of these is going to be a ground, which is going to the signal wire for one strand of LEDs. And then we've got the signal coming out of this logic level shifter. And so now if we push this over to 2D, what we should see is that now there's a ton of air wires on all of this stuff. And so now is the part where we go through and we try to place everything, but notice we've got this sort of default PCB size. We need to restructure or reshape that. If we push this to a 3D PCB, what we're going to get is, one, we're going to get a warning, and we're going to have components that are floating next to this board. The nice thing here, or the benefit here, is that there are some tools that allow us to do things like edit the board outline sketch or create a specific PCB sketch. There are ways that we can predefine this in Fusion. In our course for the game controller, we did, for example, predefine the board shape. But here, we can just push this to 3D and we can use edit board outline. Currently, this isn't at all defined. You can see these don't even have constraints. So what we're going to do is we're going to start with a vertical constraint here, and then we can put that endpoint at the origin. We can define this how Fusion would by making all of these perpendicular or parallel. And so that gives us a true rectangle. And then we can start defining the size. And so this is going to be 60 millimeters by 60. That's the final size I ended up with. We can round off the corners. So if you want to use the fillet tool, for example, 15 is way too big. 5 is probably okay. And it is not happy with me, but let's try this. And 5 and 5. We'll say okay. Fusion has gotten better about not flipping out when constraints and things go wrong. What I am going to do is I'm going to double click on this one and click on this dimension so that they are linked. So if I happen to, let's say, make it 7.5, they should all change. Go ahead and make that 5. And then I need to put some holes in here. So I think these will be 6 millimeter, and I'm going to use the equal constraint. Here's another tip for you. If you are adding equal constraints to holes, it is a good idea to always go back to the hole that has the dimension. And the reason for that, and I'll undo it actually, so I can show you this. So if I happen to make this upper right one equal to that, and then I make this one equal, and then I make this one equal, if I happen to delete that circle, then the other ones are equal with each other, but they're not equal with this first one anymore. And so if you are driving one of these holes off of a dimension, then you want to make sure, in general, in this case, we don't have to worry about too much, but in general with your design, you want to make sure you relate those back to the original. All right, so now we've updated the board shape. We need to come in and double click that feature. We're going to hold down Control and add those holes. And then we can push this back to the 2D PCB. And so we're going to update it because it's out of date. It's going to tell me, again, it's trying to warn me all the time, but we're going to allow it to update. It's thinking real hard. And now we've got our board shape. And so that's one way that we can do it, all directly within essentially the electronics workspace. The 3D model is this is a little bit of a unique thing because there are options in here to generate components and do things. One of the nice benefits of that is we can actually move components around and have it impact here. All right, so a couple things that we want to do, or generally how I work it, is I'm going to rotate the component. So I'm going to click on this one until the USB is facing to the right. And then I want to move it so that the USB is hanging off the side there. And that's, again, these were just created so I generally know where the USB is. The QT Py connector isn't needed in this case, but if I need access to it, at least I know where it is. The other thing is with these footprints, when you make a symbol that's used in the schematic, and then you also have a symbol that you make for the PCB layout, the 2D PCB. In that, you can include things like the names of the pins. And so, for example, for this, I named those pins ground. So you can see there's a bunch here that are named ground. And so that way they automatically will attach to the ground plane we create. If they aren't created that way, then you'll have to rename those specific values for those and then have it generate that connection. And so I find it easier for me to edit it in the symbol itself. The other thing that we have here is I put a label for front, and that front is going to be where we're plugging the wires in. So you'll notice that these pins are actually offset from the shape of the connector. It's just how the connector is. A lot of times when you're building these, you'll notice that they'll give you may, if you're lucky, you'll get a CAD file. If you're not lucky, you'll just have a blueprint drawing and you'll have to create this yourself. But a lot of times you'll notice that the outline, which this white is going to be the actual stuff that gets printed on the circuit board, the silkscreen layer, then you'll notice that things like that are kind of offset. And that's just because the wires actually come in between the pins to connect to that. It's just kind of the way that it's done. So anything in white here was created on a silkscreen layer, which means that it's going to get printed. And so what we want to do is keep clicking and rotate until front is on the left-hand side. And generally what I would try to do is hang this over the edge of the board. There are rules that we need to follow in terms of how close these pins, these vias and pads can be to the edge. Though the silkscreen doesn't matter. Generally, you would have the silkscreen completely on the board. But for a part like this, if I'm going to 3D print a housing, generally I would want the edge of that to maybe be flush with the outside of the plastic housing. And so that's why I tend to hang these off a little bit. And so we could potentially go a little bit further, but you'll notice that it won't let you drag up to a certain point. If you want to break that rule, those are going to be found under the rules, under DRC or design rules. So you can go into these preferences and dictate things like how close those rings can be to the sides of the board and stuff like that. I just use all the defaults. I don't ever really have a good reason to try to break a rule because without me knowing more about it, there's a good chance that the board just won't work. So I tend to just leave those. With some of the other stuff like the proto section, really doesn't matter where it is. I tend to just stick it up here. With the logic level shifter, it makes sense for me to rotate it. Let's undo that. So this is one that I didn't create, and sometimes you'll notice that the in this case, the silkscreen for the 7407 quad, or the name of it, was over that X, and that X is what we need to click on to rotate it. And so sometimes you may just need to move things around. And so with these, you'll notice there's a little bit of a U at the top. The actual chip will have that U on it, and sometimes there'll be a dot for like pin 1. This is important because it helps us identify or understand when we're putting this board together where that is. And so I'm going to stick it, let's say right there. And the last thing is going to be this voltage regulator. And now with these voltage regulators, sometimes you may want to have like a heat sink if they are getting too hot, if you're pushing a bunch of voltage through them. By default, it's going to want to stand straight up. And so what I generally do is just give it enough room to where I can fold it down. So like the board that I soldered together, I have it set like this so I can fold it down and have all this room here. There is a screw hole in these in the 3D version. And so if we push this to 3D PCB, generally that screw hole is one that you can, we're going to update it, you can screw down to the board, and sometimes you can add thermal paste or another metal heat sink to help dissipate some of that heat. When you use large components like these TO220s, a lot of times they don't have any problem with dissipating heat, at least for what I'm doing here. But if you are tending to pulse them a lot, then that could be a problem. You will notice with the proto section, there's this like black box here. That's generally because by default, it needs to have a 3D model. And so what we can do is go into the bodies and hide that, and then you'll see just the copper that's underneath it. But in most cases, if there's not a 3D model associated with something, like with the proto area, there isn't, it's just the vias, then you'll have that kind of weird by default box that encompasses the whole area. All right, so I'm going to go back to the 2D PCB layout. We're almost done. It's actually not too much more. Now that the board is set up, there are a couple of other considerations. For this version of the board, I'm not going to worry about putting the via in here. If you want to, you can place a hole, and then it can be a plated hole, and then you can run traces to it. For the purposes of our video, I'm just going to run, essentially run that 5-volt straight from here and straight to the right from the regulator. So you can see it's going 2 places. So you can see that. And there may be a potential. So if it looks like stuff is going through, it doesn't necessarily mean that those are all connecting. But just keep in mind when we get to the trace part, we want to double check these things. But at this stage, what we would want to do is create a polygon pour. And so when we go to this polygon section, there's a polygon pour, and then there's a polygon pour from outline. And if I click this, we can decide where we want to put it, the top or the bottom. In this case, let's stick it on the top. And we'll say, okay, we're going to give it a name, GND. I'm going to select from that list, so that way I'm 100% certain it matches. We're going to say okay. And so what we just did was we took the shape of the board, including the holes, and we said, okay, we want this entire area, again, based on those DRC, those design rules, we want this entire area to be represented as ground plane. And so what happens now is anything that was listed as ground, so the pin on the microcontroller, now has these red lines through them. And if we go over here, anything here that was ground, you can see those all have those like X's in them. If we go over here, anything that was listed as ground, those all have those. The pin, let's see up here, this one, that pin name was ground. Again, so these are like $P$8, $15, 22. This one was listed as ground, so it knows that it's connecting to that ground plane. So that's the first step in the process. Everything that is ground or was listed as ground is now connected. The next step is we want to connect all of these air wires. You could do this manually if you really want to, or if there are specific traces you want to do manually, then you can do them. But for the most part, you can just go into the auto router. We're going to leave all the default settings. Essentially, we can prioritize if we want it to be on the top or the bottom. We can dictate the amount of effort we want put in. For a simple board like this, there's not a whole lot going on. Essentially, what we're going to do is just let it use those defaults. We're going to say start. It's going to run through and it's going to tell you the percentage is complete. This top one's still running. The number of vias. And so essentially the via is going to be a hole in the board where the signal jumps from the bottom to the top. And you can see here, you can pick, we can go, I'll move this out to the side. We can go through and we can see which one we like as a solution. And so when I'm looking at these, for example, you can see here, it's running these traces really close to that edge of the copper. Whereas this one here, they're generally all running inside. And there's a via that's right between those those pins, there's another via over here. If I come to this one, the via is placed right between those. This via is over here all by itself. And this top one, which is the most optimized, it put the via in between the proto. And so I think I'm actually going to take the second one, and because I like the via here and not in between all this other stuff. So I'm going to say end job, and then it runs all the traces. And so anything that was placed in the top layer now has a gap in the ground. And so remember, everything red here is the ground plane. And so this signal that had to go from this RX to our fourth or extra pin, it is running on the top. And so you can see here, it's connecting right to that pin, and the ground has been isolated. Now, the fourth pin, which is this one here, is blue, which is on the bottom of the board. And so right now we're looking at the top. If we flip this over, we can see the bottom traces in blue. So this one is running up, and it's going all the way to that extra pin. And that extra pin, again, is just in case we need a fourth line or a fourth strand of LEDs. Then I'm not wasting that pin on the logic level converter. It's already been accounted for. And so that's it. That's the end of the board. Some other things that you might want to do is you might want to place, let's say you might want to place a logo. And so we can do an SVG or a DXF DWG. And so for me, I'm just going to use a lead logo. I made it as a DXF. You can use whatever you want. The scale factor, it's pretty big to start. So, cool. Wow, it's doing some weird stuff there, isn't it? And I want to put it on silkscreen top. And then we could scale it down, but let's try 0.1 again. Yeah, that's better. All right, and I'm just going to place it here and say done. All right, and so now everything looks pretty good. How do we get this out? Well, first, I haven't saved anything yet, so it's probably a good idea to save the project. And so what we're going to do is I'm going to come over here and just select save. That's not where I want to put it. I want to put it in, I think I named it PCB logic level shifter. Yep. So we'll call this PCB logic shifter schematic. And so that name should carry on. It says I violated the design rules. All right. So here we've got our schematic. We've got the 2D layout. We've got the 3D board, which we haven't pushed it to 3D yet, so all the traces haven't been updated. But since we saved it, I think it should automatically do that. Go ahead and update it. It's thinking. I'm almost out of tea. It means I need to end the video soon. Oh my goodness, it's been an hour. All right, so there we go. So the lighter green here is the ground plane. You will be able to see it underneath the top and silkscreen, just like you can see traces and stuff like that. But what's important here is that we see all of our silkscreen labels. You can see the 3D models are here. We've got our proto area, our vias. These are unplated holes, which means that they are not isolated from the rest of the board. It's just a hole through the PCB. You will notice that the ground plane does stop short of that. So some things you have to think about is like, do you need a plastic washer to hold this down? Now with this design, I actually have a plastic boss that comes through, and then the lid has a boss with a counterbore in it. So there's never a screw that actually touches this. It sandwiches the board together in a 3D print. So in this case, I don't care. If you were to actually run like a metal screw to hold this down, then you may want to use a plated and isolated area. You may want the ground plane to be skirted back, or if you have a power plane, for example. And so in some boards that I've done, I've used a ground plane on one side and a power plane on the other. So that way anything that needs to tap into 12 volts or 5 volts or whatever can do that. I'm going to go ahead and save that. And then we're going to go back to the 2D PCB because now you're probably wondering, well, how do I send this to somebody to actually make it? So first thing we want to do is come over to this little caution symbol and double check. This is like a live design rule check that happens. So these are errors that we may want to do. And errors would be if we had like an unrounded air wire, if there were two things that weren't connected. Those are potential issues. You can see here it says that there's a little red X down here. It says that action has violated DRC parameters. Switch to ignore violator in the navigation toolbar and try again. There are no errors over here, so I'm not really sure what we violated. It's potentially something too close to something else, but I think it's likely okay. We'll find out in just a second. And so the next thing is we're going to go over to manufacturing. And so there's a couple different options that we have here. For the most part, exporting the Gerber file with the drill, assembly, and drawing outputs is what something like PCB would want. It'll still give you a zip folder. You can upload that for them. If you do happen to have them build the board for you, they need a bill of materials. So they'll need things like manufacturing part numbers. Generally, that's an Excel document or a spreadsheet that you will manually fill out. They won't pull it from this. And a lot of times they will have to search their own manufacturers unless you have a very specific thing. And so, for example, the Adafruit Cutie Pie, that's not something that I would have them purchase and solder to the board. That's something that I would always purchase. But things like the logic level shifter or the voltage regulator, LEDs, resistors, things like that, some of these things they can get from multiple suppliers, and you just give them sort of carte blanche to do that. This first option here is CAM Preview. And so this is a good way for us to double check things like making sure that the vias are actually holes in the board. They're not, they're not full. Making sure that the holes that we've defined for our screw holes actually go through the board. So this is a good check. You can look at the top and the bottom side. You can focus on just the drills. And so when these boards get made, so they'll start with sort of a default board. This is a 2-layer board, top and bottom. And they'll start with the default board. They'll drill the holes. They'll machine around essentially anywhere that we've got this copper. So, for example, our top is the ground plane. They'll machine around those traces and remove the copper, and so that isolates it relative to these other things. And so with the holes, they'll drill through and things will be plated or, for those vias. But in general, we don't have to worry about that. So there's information about the board, its area, the components, the pads, the drill sizes, and number of drills, and so on. And so you can look through all this. You can look through the hole, so you can see that we've got the vias, PTH. These are basically our 4 holes in the corners, and then all the rest of them are vias at the same size. We've also got this CAM processor, which you can go through. This will give you both the ODB as well as the Gerber files and information. So if you process this job, so for example, if we select process, it'll ask you for a location. I don't need it, but I'll go ahead and save it. This is going to be in Fusion. What do we got? I'll just toss it here. So once it's processed, then you'll have things like, this is what the silk screen is on the top of the board. And so these are the silk screen around the proto area, the labels for the connector, the outline for the logic level shifter, the outline for the voltage regulator, all the labels for the Cutie Pie, the lead logo, and so on. And you can see that as well in the Gerber files. So again, the top copper. We defined the top as a ground plane. And so what it did was it machined out the areas we don't want copper, so around each of the pins. But again, if you zoom in, material was left behind to connect that to the ground plane, everything that's grounded. And then it'll go through and there'll be a document here for all the drill holes, a bill of materials, and pick and place information, and so on. So I'm going to hit cancel there. And again, what I would do for PCB, for example, is export the Gerber zip file. You can pick the location of it, and then essentially you just take that and you upload it to PCB and you get your quote. So that's that's essentially it. And I say essentially like this was quick and not an hour and 15 minutes long. But that's the overall process. And it's going to be true for pretty much anything that you do at a basic level. Now, again, I'm not an electrical engineer, but I have made several boards this way, and I have enough knowledge that I can design and make these boards for my own personal use that are like a next step above just using proto board and kind of hacking things together. And so hopefully this helps you. Again, we have an entire course on learneverythingaboutdesign.com for designing a game controller. And so we go through picking the components, picking the specific, in this case, the QT Py board that we use that is an HID or human interface device. Not all of them can be used as HID, but essentially that means that you can use it as a keyboard or a mouse or, for us, a game controller. And we go through the entire process of programming it, testing it on a breadboard before we actually build out the circuit and fusion and get the board and all that stuff. So if you have any questions on this, please let me know. And if you want to see more PCB stuff, let me know. We do have plans to do some more PCB for the GPZ series that I just have been putting off because I've had just so much other stuff going on. But I still need to finish off the GPS Speedo for that project with a Nexian display. And we've got a feather and the feathered GPS sort of top for that. And so that's something that I need to work on. I need to get to it soon. Kind of been putting it off. But if you have any questions on this stuff, I'll do my best to answer them. As always, thanks for watching. We'll see you in the next one.